Black holes, cosmological enigmas, have intrigued scientists for decades. With physics bending at their event horizons, the curiosity of what lies within has spurred a number of theories. This video explores 10 such propositions, delving into the captivating mystery of the innards of a black hole. Number 1. Singularity theory. A widely accepted view of black holes, stemming from Einstein's general theory of relativity, is the singularity theory. This suggests that at the center of every black hole is a singularity, a point where space-time curves infinitely, and matter is compressed to infinite density. This extreme density leads to intense gravitational forces that nothing, not even light, can escape. Singularity is perceived as the ultimate fate of matter that has fallen into the black hole. Once something crosses the event horizon, the point of no return, it is irretrievably destined to the singularity. The singularity behaves as a one-dimensional point in space, containing a large amount of mass. Conceptually, the singularity is where our conventional understanding of physics breaks down. The infinite densities and space-time curvature at the singularity provoke paradoxes and inconsistencies, challenging our comprehension. It suggests the existence of conditions we currently cannot fathom nor study directly, making singularity a complex topic of theoretical exploration. There are many unsolved questions surrounding singularity. Are all singularities the same, or do they have different properties depending on the mass, charge, or spin of the black hole? What happens to the information about the matter that has fallen into the black hole? Does the concept of before or after even make sense in such extreme conditions? Some physicists argue that singularities might not even exist. They suggest that the prediction of singularities might be an indication that our theories are incomplete or need modifications under such extreme conditions. So, the quest to understand the true nature of singularities remains a formidable challenge in our pursuit to unravel the mysteries of black holes and the universe. Number 2. Quantum fluctuation theory. Delving further into the mysteries of black holes, quantum fluctuation theory offers a unique perspective, steeped in the principles of quantum mechanics. This theory proposes that within a black hole, the laws of quantum physics are still intact and highly influential, resulting in significant fluctuations in energy and matter. The origins of this theory are rooted in the Heisenberg uncertainty principle, a cornerstone of quantum mechanics. This principle asserts that it's impossible to precisely measure both the position and momentum of a subatomic particle simultaneously. The more accurately one value is measured, the less accurately the other can be known. This lack of precise knowledge results in a constant fluctuation in the vacuum of empty space, creating a teeming sea of virtual particles that pop in and out of existence, a phenomenon known as quantum fluctuations. Quantum fluctuation theory extrapolates this principle to the interiors of black holes. Given the intense gravitational field within a black hole, it's proposed that these quantum fluctuations can have dramatic consequences. The immense gravity could potentially promote these virtual particles to become real particles, thus altering the state of the black hole from the inside. Quantum fluctuation theory provides intriguing possibilities for what might be happening inside a black hole. However, as fascinating as these possibilities are, they also pose significant challenges. The marriage of quantum mechanics and gravity, two of the fundamental forces of nature, is a complex theoretical endeavor. The lack of observational data from within black holes adds another layer of difficulty in confirming these hypotheses. The quantum fluctuation. Theories attempt to reconcile the properties of black holes with the principles of quantum mechanics offers an exciting vista of theoretical exploration. The insights yielded by this theory might not only deepen our understanding of black holes, but also potentially steer us towards the holy grail of physics, a unified theory that combines quantum mechanics and gravity. Number 3. Wormhole theory. The concept of wormholes in the context of black holes offers an intriguing gateway to potentially far-reaching cosmic connections. Wormholes, as theorized in Einstein's general theory of relativity, are hypothetical structures of space-time connecting two separate points in the universe. The wormhole theory proposes that black holes could serve as entrances to these wormholes. Envisioned as shortcuts through space-time, wormholes could theoretically allow travel across vast distances in the cosmos more quickly than light traveling through normal space. If black holes indeed lead to wormholes, they could potentially open up avenues for time travel or shortcuts to distant parts of the universe. The entrance to a wormhole is theorized to resemble a black hole. It would have an event horizon and exhibit extreme gravitational pull. However, unlike the singularity of a traditional black hole, where everything is thought to be destroyed, the interior of a wormhole would be a tunnel connecting to another region of space, or potentially another universe. Support for this theory comes from solutions to Einstein's field equations, the mathematical backbone of general relativity. These equations describe the fundamental interaction of gravitation as a result of space-time being curved by matter and energy. One such solution, known as the Einstein-Rosen bridge, represents a theoretical wormhole. Despite these significant challenges, the wormhole theory persists as a fascinating and influential theory of what lies within a black hole. It embodies the audacious nature of theoretical physics, providing a speculative possibility that could reshape our understanding of black hole interiors, space-time structure, and perhaps even the nature of interstellar travel. However, until we develop further theoretical advancements or empirical evidence, wormholes and their connection to black holes remain a captivating yet unproven proposition. Number 4. Multiverse theory. The multiverse theory takes our understanding of the cosmos to an entirely new level of complexity and intrigue. It posits not just one universe, but an infinite number of universes, collectively known as the multiverse. In relation to black holes, this theory suggests that every black hole may be a gateway to another universe, or perhaps the birthplace of one. This concept is rooted in the idea of cosmic inflation, which postulates a rapid expansion of the universe shortly after the Big Bang. Some interpretations of inflation theory suggest that this inflation could be an ongoing process, where different regions of space undergo inflation at different times. This process could result in a vast multitude of bubble universes, each potentially with different physical laws and constants, creating the multiverse. In this view, when a black hole forms, the immense density at its core might trigger a new round of inflation, creating a new bubble universe. From the outside, this new universe would appear as a black hole. However, from the inside, it would look like a new universe expanding from a Big Bang. This is often referred to as the baby universe theory. The multiverse theory effectively links the life cycle of black holes to the creation of new universes, implying an infinitely self-reproducing system. Every black hole in our universe might be an umbilical cord to another universe, which itself could contain black holes, giving birth to yet more universes. Despite these hurdles, the multiverse theory remains a tantalizing possibility for what's inside a black hole. It represents an audacious and profound perspective that, if correct, would radically alter our understanding of black holes, the universe, and our place in the cosmos. Though it may be an area of controversy and debate, its profound implications ensure that it continues to be an area of active research in theoretical physics. Number 5. Firewall theory. The firewall theory is a relatively recent hypothesis in the study of black holes, bringing forth a surprising and somewhat controversial proposition about what might exist beyond a black hole's event horizon. This theory contends that rather than the smooth entrance into a black hole, as predicted by Einstein's theory of general relativity, a literal firewall of energy exists, which would incinerate anything that attempts to cross it. The firewall theory was born out of the attempt to solve the paradox surrounding black holes and the loss of information, a major conundrum in theoretical physics. Quantum mechanics, the theory that accurately describes the world of the very small, insists that information can't be lost. However, black holes, as described by general relativity, seemingly erase information about anything that falls into them, presenting a contradiction. In the 1970s, Stephen Hawking proposed that black holes can slowly lose energy and evaporate over time, a process now known as Hawking radiation. While this seemed to partially address the issue, it brought forth another problem. The radiation is thermal and carries no information about the interior of a black hole. This is often referred to as the information paradox. The firewall theory was proposed as a potential solution to this paradox. The idea is that a highly energetic boundary, a firewall, exists just inside the event horizon of a black hole. As objects fall into a black hole and approach the firewall, the information they carry is transformed into high-energy particles that make up the firewall itself. These particles could then be released back into the universe through Hawking radiation, thereby preserving the information, as required by quantum mechanics. However, the firewall theory is not without controversy. The existence of a firewall would contradict the equivalence principle of general relativity, which states that free-falling objects should notice no sudden changes in the laws of physics when crossing the event horizon of a black hole. This conflict has led to the firewall paradox. Additionally, the firewall theory is not fully substantiated due to the lack of empirical evidence. As of now, observing a black hole directly, let alone a firewall, is beyond our technological capabilities. Regardless of these challenges, the firewall theory offers an innovative and daring perspective on what may occur inside a black hole. It demonstrates the vigorous efforts by physicists to reconcile two of the most successful theories in science, quantum mechanics and general relativity. This underscores the ongoing quest to find a theory of quantum gravity that can describe phenomena such as black holes more completely and coherently. Number 6. Holographic principle. The holographic principle, arising from the realm of string theory, proposes a remarkable concept that has deep implications for our understanding of black holes. This principle suggests that all the information contained within a certain volume of space can be encoded on a boundary surface that surrounds it, much like a hologram. Applying the holographic principle to black holes, we can view the event horizon as the boundary surface. The principle suggests that all the information about what falls into the black hole is stored on this two-dimensional surface, rather than in the three-dimensional space within the black hole. In essence, a black hole could be like a giant cosmic hologram, with the interior volume fully described by the information stored on its surface. The holographic principle stems from a surprising feature of black holes known as the Bekenstein-Hawking entropy, which suggests that the entropy, or the measure of disorder, of a black hole is proportional to the area of its event horizon and not its volume. This is counterintuitive to the usual volume-based measure of entropy we encounter in thermodynamics. The principle potentially provides a solution to the information paradox. If all the information about a black hole's contents is encoded on the event horizon, it can be released back into the universe via Hawking radiation, thereby resolving the paradox. The idea of the universe being a hologram might seem bizarre, but the principle has gained substantial support in the theoretical physics community. It provides a novel way of viewing space-time structure and quantum gravity. Some versions of the principle even suggest that our entire universe follows this rule, with all the information in our three-dimensional universe encoded on a distant two-dimensional surface. Despite its elegance, the holographic principle is not without challenges. The principle is derived from string theory, a framework that, while mathematically beautiful and consistent, has not been empirically tested. There is also ongoing debate about how exactly the holographic principle applies to black holes and how it might fit with our broader understanding of quantum gravity. Moreover, the idea of how a three-dimensional volume can be encoded in a two-dimensional surface is something we don't yet fully understand. Deciphering the hologram on a black hole's event horizon remains a substantial challenge. Nonetheless, the holographic principle offers a bold perspective on the enigmatic question of what's inside a black hole. It proposes a novel and profound viewpoint on the nature of information, space-time, and the fundamental structure of the universe. As our understanding of quantum gravity progresses, this principle may provide a crucial piece of the cosmic puzzle. Number 7. Fuzzball theory. The fuzzball theory emerges from string theory, offering an unexpected and radical perspective on the internal structure of black holes. This theory suggests that black holes are not defined by the traditional notions of a smooth event horizon and a singular core, but instead, they are giant, compact fuzzballs composed of strings, the smallest building blocks of matter according to string theory. The essence of the fuzzball theory lies in the quantum mechanical nature of string theory. Instead of a point-like singularity, the gravitational collapse of a star gives rise to a compact mass of strings, or a fuzzball. This fuzzball has no clear boundary or interior. Rather, its surface is a tangled mess of strings that vibrate in multiple dimensions, extending to form a structure that replaces the classical event horizon. Each black hole fuzzball has a unique configuration of strings, reflective of its history and the matter it has absorbed. This fuzzball perspective alters our view of what happens to matter that falls into a black hole. Instead of passing through a clear event horizon and moving towards a singularity, the incoming matter becomes part of the fuzzball structure, its information encoded in the vibrational states of the strings. In the context of the black hole information paradox, the fuzzball theory offers a potential solution. Since there is no traditional event horizon or singularity, information is not lost, but instead gets encoded into the string structure of the fuzzball, preserving the tenets of quantum mechanics. However, while conceptually fascinating, the fuzzball theory is built on the premises of string theory, a framework that, while compelling, has yet to gain empirical validation. Proving the existence of strings, let alone fuzzballs, is beyond our current technological capabilities. Moreover, the fuzzball theory raises several other questions. One of the main queries is understanding how these stringy fuzzballs can produce effects similar to traditional black holes, like gravitational lensing or the accretion of matter. The fuzzball's structure should also emit Hawking radiation, like a conventional black hole, but the exact mechanism remains to be fleshed out. The fuzzball theory, although speculative and far from established, represents a bold attempt to reconcile the strange world of quantum mechanics with the immense gravitational fields of black holes. It showcases the innovative and daring efforts theoretical physicists are making to decipher the enigmatic nature of these cosmic giants. As our understanding of string theory and quantum gravity develops, the fuzzball's concept may yet become a vital component in solving the mysteries of black holes. Number 8. Gravistar theory. The gravistar theory proposes a radical alternative to the traditional understanding of black holes. Instead of an event horizon and a singularity, the gravistar, short for gravitational vacuum star. Theory suggests that these extreme entities are composed of an exotic phase of matter and encased within an ultra-thin, ultra-dense shell. Gravistars were first hypothesized as an attempt to resolve the contradictions between quantum mechanics and general relativity brought up by black holes. The idea behind a gravistar is that when a massive star collapses under its gravity, instead of forming a black hole, it undergoes a phase transition. This process is somewhat analogous to how water transforms into ice under certain conditions. In the case of a gravistar, the collapsing star's matter transitions into a sort of gravitational vacuum state. This state prevents further collapse and the formation of a singularity, thus averting the infinite densities that general relativity fails to handle. This core is surrounded by a thin shell of ultra-dense matter at the gravistar's surface. Just outside this shell, space-time becomes highly warped, creating a powerful gravitational field similar to that of a traditional black hole. From the outside, a gravistar might appear similar to a black hole. However, instead of an event horizon, a gravistar has a solid surface, and objects falling towards a gravistar would hit this ultra-dense shell instead of disappearing behind an event horizon. The information paradox is thus resolved because information doesn't disappear inside a gravistar. It remains on the surface. Despite the gravistar theory's intriguing elements, it faces significant challenges. The theory's foundations involve speculative concepts in quantum gravity, a realm of physics that is not yet fully understood. The phase transition to a gravitational vacuum state and the formation of an ultra-dense shell are theoretical and have not been observed or experimentally demonstrated. Moreover, distinguishing a gravistar from a black hole through observations would be challenging, given the similar effects they have on their surroundings. Despite the fundamental differences in their internal structures, both would cause gravitational lensing and could have accretion disks. However, despite these hurdles, the gravistar theory is a fascinating example of the creativity and persistence of physicists in seeking to unravel the mysteries of the universe. By offering an alternative vision of these extreme objects, the theory contributes to our ever-evolving understanding of black holes and stimulates further research in the quest for a theory of quantum gravity. Number 9. Planck star theory. The Planck star theory introduces a revolutionary proposal for the inner workings of black holes. Rather than housing a singularity, this theory posits that black holes might contain highly compact stars, known as Planck stars, made from quantum gravitational effects. Planck stars derive their name from the Planck length, the smallest measurable distance in the universe, and the Planck time, the smallest measurable time unit. Both are foundational concepts in quantum gravity. The theoretical framework sought to reconcile general relativity with quantum mechanics. The Planck star theory is rooted in the concept of quantum bounce, which is tied to loop quantum gravity, one of the leading approaches towards quantum gravity. The idea is that when a star collapses under its own gravity, quantum gravitational effects become significant, preventing the formation of a singularity. Instead, the collapsing matter rebounds in a big bounce, leading to the creation of a Planck star. Planck stars are extreme entities. They are incredibly dense, with masses comparable to black holes but sizes near the Planck length. They also have lifetimes on the order of Planck time from their perspective. However, due to the immense gravitational time dilation, these tiny transient objects appear to exist for billions of years from an outside observer's standpoint. Within the context of black holes, a Planck star would form and then gradually grow, converting the black hole from within. Over a colossal timescale, the Planck star could eventually consume the entire black hole, leading to a transition from a black hole to a white hole, an entity that expels matter and energy instead of absorbing it. The Planck star theory offers an intriguing solution to the black hole information paradox. As the information is not crushed into a singularity, but instead rebounded back, there's no fundamental violation of quantum mechanics. Nevertheless, the Planck star theory faces significant challenges. It depends on the validity of loop quantum gravity, which, despite its promise, is still a theoretical framework without experimental confirmation. Moreover, directly observing Planck stars is currently beyond our reach, as the Planck scale is incredibly small and the process of a black hole turning into a white hole is expected to take an enormous amount of time. Yet, despite these hurdles, the Planck star theory represents an exciting and imaginative idea within the field of quantum gravity. By offering a novel perspective on the interior of black holes, the theory encourages us to push the boundaries of our understanding of the cosmos, inviting further research into the quantum realm and the nature of these mysterious celestial objects. Number 10. Information paradox. The black hole information paradox is a long-standing puzzle in theoretical physics that arises when considering the fate of information that falls into a black hole. The paradox stems from the apparent conflict between general relativity, which describes the gravitational behavior of black holes, and quantum mechanics, which mandates the preservation of information. In the context of a black hole, information refers to the complete description of a particle or object's properties, such as its position, momentum, spin, charge, and so on. According to quantum mechanics, this information must be conserved, meaning it can never be created or destroyed. However, black holes, as described by general relativity, seem to defy this rule. When an object crosses a black hole's event horizon, it appears to be lost forever, with all its information seemingly erased. This scenario suggests a fundamental conflict between general relativity and quantum mechanics, the two pillars of modern physics. The situation became more complex with Stephen Hawking's discovery of black hole evaporation, now known as Hawking radiation. Hawking proposed that black holes can slowly lose energy and thus mass over time by emitting thermal radiation. Intriguingly, this radiation does not carry any information about the black hole's interior, implying that when a black hole finally evaporates completely, all the information it contained is lost. This result directly contradicts the principles of quantum mechanics, leading to the information paradox. Since its inception, the information paradox has sparked intense debate and a multitude of proposed resolutions, involving concepts like firewalls, the holographic principle, fuzzballs, gravastars, and Planck stars. Each of these theories provides unique perspectives and potential solutions to the paradox, from suggesting that information is encoded on the black hole's surface or transformed into new states, to proposing radical revisions of black holes' interior structure. Nonetheless, the paradox remains unresolved, with none of the proposed solutions gaining universal acceptance. The central problem is the lack of a complete theory of quantum gravity, which would reconcile the laws of quantum mechanics with those of general relativity and provide a definitive answer to the paradox. While the information paradox poses a formidable challenge, it also represents an invaluable opportunity for progress in theoretical physics. The paradox points towards new, uncharted territories of physics, highlighting the need for a more profound understanding of quantum gravity, the nature of information, and the true structure of black holes. This quest for resolution continues to inspire innovative theories and stimulates the advancement of our understanding of the universe's most extreme objects.